Well, good evening, everyone. We've got a long schedule today since there's only really one teaching day this week and we have so few weeks. So we're going to get 6.3, 6.4 and 6.5 covered today. So depends how quickly we do them, but my goal is we're going to get them finished. So if we need 3 hours and 40 minutes, then I guess that's what we'll have to do. So there's going to be a lot to take in. Your homework, God, that's just what my brain is like. Those 6.3, 6.4 and 6.5 is the homework assignments that's due by the end of Sunday. So that's kind of what you have to get done. Also, I mentioned it, but some of you may have came in late. Sometime today, probably at the end of this first chunk, I'll try and break it into 3 chunks or something like that. I'll be doing a verification of your participation grade, so we both agree that it's the same number. And then once that's done, I will be sending you by email what your grade is. Not just your midterm grade, but the whole thing, your homework, your participation, your midterm, combined using the weighting that we have, which is 30% of your grades homework, 20 is your midterm and 20% your participation. So let's look at this. How do you find the area under any normal distribution? Well, what we looked at last time was a normal distribution called the standard normal distribution. That's basically the Z-score one. And when you looked at the Z-score one, you looked at pictures that look something like this. And we could use what was on our calculator, a really cool thing called the normal CDF. And it had 2 numbers, and then it had the mean, which was 0, and the standard deviation was 1, right? Now you could use this to find areas to the left of a Z-score, areas to the right of a Z-score, or the areas between. Those areas are actually the percentage of time that that would happen. So if you can imagine that about here was negative 1.5, if you're being asked to find what percentage of Z-scores are, say, less than negative 1.5, the normal CDF for that would be negative 999, which is a special number I created, and negative 1.5, and then you went in and you hit buttons on your calculator and you get your answer, right? Now, that was 6.2, and it's designed for only Z-scores, right? That's shapes where you go 0, 1, 2, 3, 0, 1, 2, 3. But we want to see, can you use this guy to do any normal distribution? And the answer is yes, and it's a very simple transition. You don't need to do much more. In fact, if you wanted to use this technique, didn't you have to turn things like if the mean was 50 and the standard deviation was 10, and you wanted to find what percentage of people, had an X between, 40 and 63, didn't you have to turn these into Z-scores? And then you could use that. That was kind of the strategy. And actually, that's redundant now. So let's do this as our first example then. Suppose there was a test and the mean score was 50 and the standard deviation was 10. So you could imagine what that shape was. It's a normal distribution. There's 50. If you do 1, 2, 3 standard deviations going forward, that's not a negative 40, 30, and then finally 20, it would look something like that, right? Suppose we wanted to know what percentage of people, right? So what's the percentage of people who got a score bigger than 73? Right, it's a bit like Z bigger than 2, right? That kind of question. Suppose our second question is, we'd like to know the percentage of people who got a score less than 52. And the third one is, we'd like to know what percentage of people got a score between 32 and 51. Well, what we're going to do is we're going to use this fella. We just change the information a little bit. For instance, in this one, you're going to go normal CDF. And you are going to do low, high, mean, standard deviation. That's its format. So let's see what that looks like. It's going to be the normal CDF. The small number is 32, low. The high number is 51. The mean is 50. And the standard deviation is 10. You put that package together, the calculator will tell you the percentage of scores now between 32 and 51. So we've pretty much done that. In fact, I think it was this class. Somebody accidentally went and found out, or deliberately found out, do you know you don't need to do this? If I just put in the real numbers, I get the same answer? I can't remember if it was this class or not. And the answer is yes, you can. So I'm going to have a bit of luck here. Screen 2. There. So what you're looking at, or should be looking at right now, are two calculators. The one on the left is a TI-84, the old kind. The one on the right is an emulator that will be more like a new calculator. So you can see, they're basically the same, but they work slightly differently. So let's do it on this one first. Oh, don't you start doing that. Okay. Can you still see two calculators now? I've moved some stuff. Oh, thank goodness for that. Okay, so we're on. You go second distribution. You want choice number 2. You hit enter. In this case, the small number was 32, comma. The big number is 51. The mean was 50. And the standard deviation was 10. And then you just hit enter. Oh, shoot, I forgot to put in a comma there. So let me try that again. Second distribution. Number 2. Can you see I forgot to put the comma there? So, where am I? 32, comma 51, comma 50, comma, got it this time, 10. There, that's it done correctly. And the answer is, as a decimal, 3 decimal places at least, 0.504 when you round it off. And that is 50.4%. Which is what? Roughly half the class would get a score somewhere between 32 and 51, right? So that's what we're being asked to find. We got it. Now we've got these other two. So I'm going to return back to these, and then we'll use them on our calculator. Were you okay with that? Was it seem, what you would expect it to be? That the normal CDF can do the job for any distribution. It's not just the, the 0-1 distribution. Right, let's look at this fella. I think I've given it enough room to squeeze it in. It's going to be normal CDF. There are going to be two numbers, a low one and a high one. Then there's going to be a mean, which is 50 in this question, and a standard deviation of 10. Okay. Suppose you want scores less than 52. What kind of numbers do I need? Let's phrase it this way. Where should the 52 go? Should it be the first number or the second? If you want less than 52.
Be the second number.
Right. Now, this number here is kind of artificial. Didn't I make it up? I just said this is a number we should use. What is this first number going to be?
It would be 0 because you can't score less than 0.
In common sense, yes. And that probably would be okay. But in general, we use the same number all the time. So I'm just trying to keep it standard. So even although this number is impossible, I still use it. Negative 999. You remember that number? Negative 999. And do you know what the next one's going to be? Positive 999. Now, by doing that, I don't need to think about which numbers are realistic, which numbers can't happen. You just use negative 999 in all of the stories that are less than, and then you don't think about it anymore, right? It's just a way of a convenience. Right. Are we comfortable with that then? Do you remember the negative 999 trick? Right. What about this fella then? I want to get find the percentage of people who scored 73. Now, you know, if I was doing 73, it'd probably be that piece of the cake here, right? Visually, out there, 73. So it's going to be a normal CDF. The last two numbers are the mean, which is 50, and the standard deviation is 10. And we have two numbers. 73, right? Does it go first or does it go second? In this situation, where do you put the 73?
First.
Yeah. Now, hopefully this next question is a lot more sensible. What made up number do you fill in here as a standard number to do all of these kinds of questions?
999.
Do you see how it works? Well, for me, anyway, do you see how it works if you just use the same number in every story? Because you could say, well, nobody's going to get 100 in the test and things like that, but who knows? The test could have been out of 200, right? It could have been a really hard test. So, yeah, 999 probably is going to cover more situations. Now, these two fellas here now become a calculator question. So I'm going to zoom over to my calculator world. And I'll clear this one out. And do you know what I forgot to do? I forgot to show you what it looks like on this one. So I'm going to do it in both of them this time, and I won't forget. Second distribution, choice number 2, hit enter. So I'm going to do the less than 52 one. So the less than 52 was negative 999, a comma, 52, a comma, 5010. Looking good? And let's see what that ends up being. That ends up being approximately 0.579, which is 57.9% of the people in the class got a score bigger than 53. That's kind of what it means in English. And the other one was the less than. Let's do the less than using this one. So it's going to be second distribution, number 2, enter. But in this world, you see that you get a table rather than you type the numbers in, so it's a slightly different format. Now, in less than 52, the low number was negative 999, all the way up to 52, with a mu, which is a mean of 50, and a standard deviation of 10. And then paste, paste. No. There's a shock. It's the same answer. Because it's actually the same question now that I look. Right. Which is, you know, it works. You see, it's the same answer. Right, I guess I should have done the bigger one. That's the one I forgot to do. So let's do a bigger one. I've got this one set up, so I'll do it on this one. Second distribution, number 2. And for bigger than, you do 73. The upper number is 999. I can keep the other 2 because it's the same number. I can hit paste and boom. And the other answer is 0.01. And that ends up being really about, what, 1%. So what we have here is a very convenient way of calculating any percentage to do with a standard normal. We can find out what percentage of numbers have a score bigger than 72 or 73, what ones have a less than a score of 52, which ones have a score of between, say, 32 and 51, and any other number you like, right? Bigger than, less than, and between. Basically, isn't that all you would ever typically want to know, right? Now, what percentage of people have higher than this, lower than this, and so on, right? Agreed? Any questions? Okay, that's a good sign. Right. So my second example. My second example, I'm going to use my favorite IQ tests. The mean is 100 and the standard deviation is 10. And if I did an IQ test, its normal distribution would look like this. When you draw sketches of normal distributions such as this one, why do you stop at 130 and, oh, it looks like a 90, and 70? Why don't I go further, or maybe only do, I don't know, that much? There is a kind of reason behind that.
Is it simply just because there's 3 standard deviations away and there's unlikely to be any data outside of that?
Yeah, almost everybody is within 3. So isn't that basically almost everybody, everybody's IQ accounted for? So yeah, that's the reason. 3 is a kind of magic number in these, isn't it? 3 standard deviations either side is almost all. Or if you want to be really precise, 99.7%. Right? That's the number attached to what they call almost all. How much would be between here and here, which is 2 standard deviations? Just a little memory check for you.
68%?
Oh, go the next one up and you've got it.
Go the next one up?
Yeah, 68, 90.
Was it 99.7?
Oh, this is like you hitting too far and then not hitting enough. You're giving every answer I want except the one I want, right? Right? So if you do everybody, the almost all, that is 99.7%, right? And if you do 1 standard deviation either side, that's the 68% that you gave me. Now there's one in between those 2 answers, which is the one I was asking for. So go for it. What's the one that's left?
95.
68. Yeah. Can you remember those 3 guys way back in the day? Right?
I'll never forget the 95 again.
Oh, then my job is done. So that's all I need to do. Pick on you and you'll never forget something.
Yeah,
Okay.
I guess so.
Right? Well, that means that this class is in for a really rough 3 weeks. If that's the teaching strategy, I have to be horrible to you to make you remember some. I love you. I'm going to pick on you next then, right?
Yes, boys.
I know.
Okay, then I better not push it. So back to this question. We can get more than just these guys, right? Now that we've got this really cool function that's on our calculator called the normal CDF, can we get IQs bigger than anything, IQs less than anything, and IQs between anything? Agreed? Right. So here are 3 questions. What's the probability that you get an IQ greater than 123? Second one's going to be, what's the probability, what percentage is equivalent, of getting an IQ less than 91? And the last one is, what's the probability that you get an IQ between 80 and 120? And I'm going to let you go hunting for your calculator, and hopefully you'll find it in the next few minutes, or your emulator if you're using it, and I'll let you have a shot at it first, and then we'll do it. So go for it. You have got 90 seconds, 30 seconds each. Okay, and you can catch up with me. Hopefully you have time to do at least one of these. When you look at, say, this question here, you're going to use a normal CDF, and all three of them you are. But and the first thing is, do you notice that the last two numbers are always the mean and standard deviation? So really you only have a choice of what do you do for the first two. Now, when it's a bigger than, doesn't the first number go there and you finish with 999? When it's a less than, don't you kind of switch places? Your number goes second and negative 999 goes first. You see the format? That's what a greater than always looks like. The number 999, right? So greater than 82 would be 82, 999, right? Greater than 55 would be 55, 999. Now, if you want to do less than, isn't it negative 999, the number you're trying to be less than? In this case, it's 91, but it could be 22 or whatever. And the between one's probably the easiest one, because it's kind of what you see is what you get, isn't it? It's between 80 and 120, and that's just two start and finish numbers. Are we comfortable about how to take this and turn it into what the normal CDF calculation that would get you that answer? Excuse me. Come on, let's go. Bye-bye. Okay, so let's do it. That was our dog. I think she wants attention because I took her out before. So I know she doesn't need a poo buck. She's just being a little bit needy because she can be. Right. Do you want me to do it in the old calculator or the new one? I'm talking about doing the first one, question A. Old calculator or new?
I'm using the new one. That works for me.
Okay, so we'll do a new one then, at least for the first one. Are most of you using a calculator that does the menu choice where you type things in, the new one as we're calling it? Are most of you doing that kind of calculator? Because maybe I should focus on that. I don't know. Okay, there we go. Choice number 2. Good. Hit enter. In this case then, it's 123 or bigger. The mean is going to be 100. And the standard deviation is also 10. And the answer I get here for greater than 123 is 0.011, which is about 1.1%. So do you know if you've got an IQ, if you ever did your IQ test and it's 123 or better, do you know that you're in the top 1% of all Americans as far as IQs go? Right, so pretty impressive, right? Now, second one, less than 91. Second distribution, normal CDF. Now, the less than story has a negative 999 first. And then since you want to be less than 91, that goes second. The cool thing about this calculator is don't you just hit enter a lot if all the numbers stay the same. So it's a little bit quicker. And this time I get about 0.184, which is about 18.4% of Americans have an IQ less than 91, most of which I believe play football. And last one, I always get that again. Last one, here we go. And this is a between 80 and 120. So between 80 and 120. And the mean is still 100, so I'd leave that alone. This sigma, the standard deviation 10, I'll leave that alone. And then I paste. And I go boom. And the answer here is a very big number, 0.954, which is 95.4%. Now let me come out of here. And we'll return to our whiteboard. And you will see something. When I said 80 to 120, wasn't that basically from here to here, right? From 80 to 120. And isn't the answer, at least we were told the answer was 95%? Did it end up being 95%? Yeah, pretty much, right? 95.4%. So do you know that 95% didn't just get made up? I mean, it does exist, doesn't it? You could always check it. So if you ever forgot what 2 standard deviations were, couldn't you just go and do a normal distribution and pick a number to the left that was 2 standard deviations away from the mean, and then pick the number to the right and do this on it? And you would say, okay, it's probably 95 then. Now, I don't have time to do it, but see if I did from 70 to 130. I already know the answer. 99.7. The almost all, as the textbook calls it. It's kind of nice when you can see the magic of why this happens. If you did 90 to 110, do you know the answer will be pretty much 68%. You know, it might be 67.9 or 68.2, but it'll be rounded off at 68%. The advantage of this is we don't just stop at these numbers. Can't we get any percentage bigger than any number, less than any number, or between any number? Okay, I think I'm flogging a dead horse here. Are we good with these? And I don't need to, you know, just keep doing it until you get bored listening to me. Are we comfortable with bigger than, less than, and between using the normal CDF? Right, good, because I'm happy you're happy. So let's look at a rather obvious question that ends up not being so obvious. I'm going to collect some data from you, if you don't mind. And we're going to use this data to do some analysis. So I'm going to collect your data and we're going to find its mean and standard deviation. And then we're going to use the mean and standard deviation, and we're going to do a couple of the questions that we just did with the normal CDF, and then we'll see how accurate it is. And then we'll show you why it's a problem. We're making a very big assumption in these questions we've done, and that is that the distribution is a normal curve, right? A bell-shaped curve. Do you know if the data is very skewed to the left or very skewed to the right, the numbers that we just got will not be accurate, right? They won't fit reality. And so it is important, as you'll find, that that works. So if you wish to share, you shall do so. If you do not wish to share, then you're totally entitled not to. So I'm going to ask for ages in a few seconds. I'm just getting the screen opened up a little bit. There we go. And okay, we'll start in the teens. Anybody teens?
I'm 19.
19. Just shout out your name, whatever you are. Nehemiah.
Lauren.
Lauren, you get your age. But Nehemiah had his hand up, so all you do is shout 19.
19.
Right? 19. Oh, two 19s. Any 20s? 20-somethings?
29.
29. Laura, it looks like, Lauren, you were asking a question.
I'm
Go for it.
20.
Go for it. What are you, Lauren? Get it out.
Sorry, 18.
Right. Finally got, God, 18s are always a pain, aren't they? Right.
24.
We got a 24. Anybody else want to chuck in the 20s?
27.
26.
27, and I heard the 26. Anybody else?
26.
Another 26. Anybody else?
22.
23.
22 and a 23. Anybody else? Okay, any 30s amongst us that wants to? You may have said something. 30 something? Could somebody catch that and repeat what they said? 32. Anybody 30s?
31.
Yay. Any 30, anything else's? Any 40 somethings?
45.
Any 50 somethings? Okay, there I am, right? That's about everybody who wants to participate, and that is fine. In the statistics world, I would add these up, and I would add up the class, and let's pretend there were 3 people. They are called non-responders, right? They voluntarily chose, which they were totally entitled to, so don't vote for them now, right? You had your chance, it's gone, that's fine. But they're non-responders. If those non-responders are random, in other words, there's a 20-year-old one and a 32-year-old and whatever, it wouldn't matter, right? It would just be a reduced data set. But let's suppose non-responders are people who don't like sharing their age and they tend to be older. Then can you see that my sample would be weighted against that, right? I'd have fewer older people than truly exist, right? So non-responders could affect the validity of this data. I don't think it does in this case. So what am I going to do? Well, it's a whole experiment. So can you imagine that this wasn't just you? I would like to know the average age of every American. Excuse me, I'm going to have to mute everybody because we are getting some background noise. There we go. So where was I? Here we go. So imagine this was all Americans. So I can't ask every American your age, right? It would take forever and a day. I don't know. Do they ask you in the census your age?
They pared it down a lot this year. I remember like the previous census in 2010, you know, they wanted to know everything. But this one, I think it was just your age, your ethnicity, and your name. Or not your name. No, that's the one thing they don't ask.
Yeah. So age and ethnicity, and that's it. Am I allowed to put Scottish in?
No, you are not allowed.
Why not?
I know. I always write in Australian, but nobody seems to think that's terribly funny.
Huh. See, I'm Celtic, and Celtic is actually a race. Germanic as a race. I mean, we're all Caucasians, but my race is Celtic. I'm quite proud of being Celtic. I mean, it's a couple of thousand years old. It's a good racial group. Yeah, kind of
So
feel
that's
left out.
government.
Yeah. In Britain, you tell people if you're Scottish.
Why? Because they'll come and find you if you don't.
They probably do that anyway in Scotland. They're pretty mean. Yeah. Okay, so focus here. Imagine this is a bigger sample. So I went out and I didn't just get 2, 4, 6, 8, 10, 12, 13. That's an unlucky number. I got 13 people, but I got 13,000 people, right? So imagine I got a really good sample. Wouldn't I be able to use that to make predictions about the age distribution of Americans? Now, I've made a couple of assumptions. This data is definitely American adults, right? And, 17, 18, right? Adults. I'm not collecting data on high school students, right? Or children. And that's fine. My population is adults. That's all I make it. So I'm going to find the mean, and I'm going to find the standard deviation of this data. And that is then going to allow me to make some predictions. So I'm going to figure out what percentage of people, based on this sample, have an age that's greater than 49? What percentage of Americans are going to have an age less than 19? And we could do others, but I won't do the others. Right. So the first part's going to be a little bit laborious, but it's good practice. I'm going to go into the calculator, and I am going to calculate the mean and standard deviation, but I am not going to do it by hand, right? I'm going to let the calculator do it all for me. So it's been a while since we did that. Can you see the screen with the two calculators? Because I'm weird-armed. Okay, so pretend it's not a problem. Right, let's do it on this one here. If you want to put the mean and standard deviation into a calculator, let's get the cobwebs out. What button do I have to press to get there? I'm about to get the mean and standard deviation. I need to get that data in there, don't I? Can you remember what button to start the whole thing going?
It's stat, no?
Yeah, you're correct. It's the start button. I guess you could just hit buttons until you see a screen. Oh, it's that one, right? I guess that's the alternative. But right, and would you agree it's number 1 edit? So you hit enter. And in L1, I'm just going to put that data. At least I'm going to put what I've got in front of me. And if I screw it up, then we'll just pretend I didn't. So there was an 18-year-old who was continually trying to vote and nobody would let her. And then we have a 29-year-old and a 24-year-old and a 27. Does the calculator care that I'm putting these numbers and they're not exactly in order? No, doesn't care a bit, which is good because it's one less thing we have to do, right? Okay, so there's my data in, and it is 13 numbers. Do you see L113 is 61? So I know I have 13 numbers. There's 13 numbers. I haven't missed anybody, right? It's a quick check. Now, what button do I now press to find the mean and standard deviation?
It's stat again.
It is stat again. Then where do I go?
Calc.
And you see in this case, it's got a guy called one variable stats. That's where it's stored. So you hit enter. And in my case, you have to type in L1 because that's what that little black flashing cursor is asking for. And in my calculator, blue button 1 gets you it. So I'm just telling it where the data is stored. It's stored in a column called L1. So when I hit enter, we'll get tons of stuff. But the only stuff I want for this question is the mean, which I'm going to call 28.5. And the standard deviation. Okay. Don't we have 2 standard deviations here? One of them's 12 and the other's 11.5. And I'm hoping I mentioned this. Isn't the top one called the sample standard deviation? And the one underneath it's called the population standard deviation. In my story, wasn't it a sample I was using? It was just a bunch of years. It wasn't everybody in America. So that's why I'm choosing the 12.01, which is basically 12, isn't it, if you round it off? So that's like phase one done. We've collected our sample. So you lot are going to represent adult Americans, and the average age is 28.5, and the standard deviation of this sample is 12. I should be able to use it then to calculate these things. I'm going to use it to try and estimate how many Americans are older than 49. Now, isn't this a normal CDF question? So we're returning to normal CDF. Now, if you want to be bigger than 49, I'm putting in the last two numbers because they're kind of obvious, right? Bigger than 49, first or second place?
49 will be first.
And then a whole load of nines, right? And then this second one is a normal CDF. And this time we're talking about less than 19. So won't it be negative 999, comma 19, mean and standard deviation? Do you see that once you've got a data set, don't these numbers become pretty much fixed? Right, you use them all the time. And then for these ones, so I'm going to get these two guys, I'm going to just do it on this calculator for speed. And then we're going to check using our original sample whether they match well or not. And here goes. So if you bear with me, second distribution. If you're doing it with me, that'd be great. So if I screw up, you can tell me. So there are 49, a comma, 999. My calculator's the old guy, so I have to hit in the thing with all the commas. And I am looking at, I'm doing red, about 4.4%. It ends up being 0.0437, but that's 4.4%. Now I'll do the other one. And it's negative 999, comma 19, comma 28.4, comma 12. And I am looking at about 21.7%. So what I am doing here is I am making a prediction that only 4.4% of Americans are bigger than 49, and that 21.7% of Americans are less than 19, at least based on this data set. So I'm going to do a check on it. Let's do the greater than 49. Greater than 49. There's only me out of 13. And 1 out of 13 ends up being about 7.7%. I'll put that in it, 7.7%. And this fella here, well, if we look at the data, who's less than 19, you count 19 as well, typically. So that's going to be 3 people out of 13. And the answer I get is about 23.1%. It wasn't too, I mean, it was what, 1.3, 1.4 out. It's not bad, right? It's not great. Horrible. Agreed? I mean, it's almost double what it should be, right? 7.7 should be 4.4. What that is telling me superficially is that this data isn't really normal. It's probably skewed to the right. So here's my justification for that. Can you imagine that we nailed the average, that it is round about there, right? If you go to this side, and someone mentioned it, aren't newborn babies the end of the line? You got born today, your age is 0. On the other hand, if I do this to scale, so there's 20 and there's 10, right? And there's 30, there's 40, 50, 60, 70, 80, 90, 100. You might even get 110. Can you see, just by the nature of things, won't this data probably be skewed to the right? Now, when data is badly skewed, you cannot be comfortable with your predictions. On this side, it was pretty good because kind of on this side, isn't it quite symmetric looking? On this side, it was horrible, right? It was almost twice. But can you see it was because of the skewedness of the thing? So we need to be able to tell if our original data is normal or not, in which case you can be comfortable with your predictions, or whether it's badly skewed in some way, in which case you probably shouldn't even do this because you're kind of guessing in a way, aren't you? I'm guessing that it's 4 and it really was 7, right? I'm guessing. It's not good to guess. You might as well just throw a coin and say, yeah, 8%. You know, I just guessed. Right? It's just as accurate, right? It's not a very good way. So how do we tell? Well, if you collected this data, can you imagine I collected a lot of it? Then I could probably couldn't I probably put a little histogram and it would look like that? You know, if I collected 10,000 ages. So I don't know, you'd have the 0 10s, right? And then the 20s, and then the 30s, and then the 40s, and the 50s, and the 60s, and the 70s, and the 80s, and the 90s. Okay, you got one person who was 100, right? You got up to there, right? Can you see that the histogram would be one way of finding that? You could just take your data and make a histogram of it. And part of doing a histogram is that some people like to put like a curve through it. It just helps you visualize it. Well, for some people it does. And unfortunately, this is good if it's definitely skewed right. You know, if it's skewed right or skewed left, and it's definitely right, really badly skewed left and right, won't you notice it? I mean, a really badly skewed right is kind of hard not to notice. But suppose it's kind of sort of a skewed right, right? Approximately skewed right, especially when, you know, the data doesn't go up and down like a nice ladder, doesn't it? Can go up and then a little kink down and up, up and down and up and down. You know, it kind of randomly moves a little bit. You know, the kind of real data is never perfect. It kind of does little step ladders all the way up and down. It's much harder to tell, isn't it? And histograms, our brain, unfortunately, is hardwired to see patterns. So we will see what we want to see. We will see normal in histograms that probably aren't that normal, right? You kind of ignore the little bumps and you say, well, like, kind of, I want it to be normal. I kind of see normal. You know, if you look really hard at the moon, you see a face, right? True story. I don't know why this came out. I was watching a TV program. Chinese people don't see a man in the moon. They see a rabbit. And I saw a rabbit once. They told me that. Right? The program was showing you, you know the big craters that make the eyes and the thing, and you know that's why we see a man. But evidently, when the Chinese see it, at least the astronomers saw it, they saw a rabbit. You know, kind of cool. Have you ever looked at a cloud and saw a person's face, or a rabbit, or a dog, or a something? Have you no imagination? Because I have.
I'm looking at it right now, and I totally see it now.
Yo, you see the rabbit?
Yeah. People have gone and like traced around it. Yeah, no, I see that. I see that more than I see a man. I can't see a man there, but I see the rabbit.
Do you see what we've done to your poor brain? Is your brain has now been hardwired to see a rabbit every time you look at the moon. Right? So when you look at a cloud, you see what you want to see. Don't you just take bits that are vaguely leg-like and boom, you've got a dog, right? Or you take bits that have this. That's the problem. We can't rely on pictures. We need another technique. And you only get one shot to do this technique. So I want to show you how it works. Do you see all the data that we've got here? Can you imagine every single one of these I could turn into a Z-score? Right, so 18 could be turned into a Z-score, right? Wouldn't you go 18, take away that, divide by 12? Remember Z-scores? X take away mu over sigma. So on the x-axis, you do the Z-score of each number. And we know that Z-scores typically, don't they go from 0, right? Yeah, from -3 to 3, right? And then on the vertical scale, you put the raw data. And so what you do is you take 18, so what's the smallest score? I've got 18, so I'm going to go 10, 20, 30, 40, 50, 60, 70. And for every single one of them, so there's me. Let's say my Z-score is 2.5 and my real score is 64. Do you see that would be the dot that goes about there, right? Now this person's 45. Let's say their Z-score is 2 and 45 would get me to about here, right? And then everybody is Z-score against a real score, right? Z-score against a real score. And if you get a sequence of dots that look curved, then your data is not normal. If, however, you get, and life is not perfect, but if you get a straight line, the data is normal. Now, I know you're going to say, well, not everything's straight, you know, but that's much more curved and that's much more straight. Would you agree that our brain is designed to see straight lines and it's designed to see curves? So it will home in on one or other of those two shapes much better than I always want to see normal even when it ain't, right? So we have this little diagram. You never get to create it. If you wanted to do it, if you were a, you know, if it was your job to be a statistician and you've collected a whole load of data, this would be part of your initial analysis, right? You get the software to do a histogram so you get a feel for what it looks like. You get the software to do one of these ones, right? And if you saw a straight line, you would go, great, because when I publish my paper, I will put that in the appendix. Look at Appendix 4. See the straight line? That was normal. That's why I could do all these calculations. That's why I predicted from my sample what the real answer would be in the general population. Now, if you did this and it was curved, and then you went on and you did all this stuff, isn't this stuff fraught with errors if it's not normal? And then people would say, well, actually, it'd get peer reviewed. All peer review does is that you put in a paper saying, I've discovered some cool stuff, right? I've done a survey, I've done a sample. Here's my analysis. Here's everything to do with it. Here's what I've found out. And then other medical people, if it's a medical world, science people, physics, if it's a physics world, right? Whatever it is, they peer review it. They look at it. So if I was doing a peer review and I looked at their thing, I would say, okay, page 1, I'm going to stop looking. If I know that he's been using normal distribution, this normal CDF, on data that look like this, wouldn't you be highly skeptical about the accuracy of his predictions? And so the poor guy would get, it would get kicked out. I would be signing off his peer review and saying, not validated, right? What he said is not validated. It's not good science. We won't publish it. There's been a lot of really sneaky things happening lately. Have you noticed that, especially because of COVID, there's been lots of, I don't know how they phrased it, non-verified surveys and data that's coming out? So they haven't been peer reviewed yet, which means it hasn't been checked that anything that they've said is actually valid. So they've came out and they'll make something up and say, hey, do you know that this new drug is really good at reducing the amount of recovery time for a COVID-19 patient, right? There's good evidence that it's working well, right? You know, that kind of report. That's not being peer reviewed yet. And yet those reports are going out. And the worst thing about that is that, see if people who peer review it look at it and say, you did a bad experiment. I could do a bad one right now. Suppose I've got a drug that I like because I've got shares in it. Let's be unscrupulous. Couldn't I do a survey where I get 200 patients? 100 just came in early stages of COVID-19. The other 100 are on respirators and are really, in a sorry state. Okay? Couldn't I give my drug to the healthy group and use as the placebo, but it wouldn't really be a placebo, whatever drugs they're using on the other group? Wouldn't my group have a bigger success rate than the poor invalid group? That's not a valid experiment, is it? They've kind of broken every rule in the world. But couldn't you get a good newspaper story out of that? So nothing should be published that isn't peer reviewed, because if it is, people then get an idea that this drug is great. And then the peer review comes out, and you never hear about the peer review. Isn't it the way that media works is they tell you a story, and then on page 1, and 2 weeks later they apologise in one line in page 27. So they put a big story about drug A, how big and great it is, and then you never hear anything. And the chances are you never heard anything is that after it got peer reviewed, the evidence wasn't there. Your sample size was 14 people. How on earth are you going to make any conclusions on 14 people, right? Can you just get lucky? Wouldn't the 14 people probably recover if you just gave them a sugar pill? How do you know? Don't you need big sample sizes, 2 separated group, double-blind experiment, the whole 9-yard stuff? Now, before you get too depressed, there's a really good one in the Lancet. It's been peer-reviewed. And it looks like AstraZeneca is the name of the company, but they're working along with Oxford University. Oxford University has got big prestige in Britain, right? It's one of the oldest, most prestigious universities. They are not going to sign off on bad science, because won't that reflect on their university and their prestige? And they've looked at the data, and they're basically the people organising the structure of the, collecting the data and doing stuff. And it looks like that's good data. It's early stages, which is fine. Stage 1, just to, I'll carry on here, because the medical people are interested. Stage 1 is typically, you test to see if the new drug is dangerous. That's its main job. And it's past phase 1, right, stage 1. A couple of people got headaches, a couple felt nausea. But that could have been they had a drink last night, right? You can't blame the drug every time, right? So it's safe. Nobody's killed over and died. If you gave a drug and 15 people dropped dead with heart attacks, that would be the end of the experiment, right? You wouldn't use it. It's dangerous, right? Phase 2 is very often done alongside it. And phase 2, in this drug, the evidence is that it's producing antibodies, which is good. That's how your body figures out that's bad and it goes and kills it. And it's also producing T cells, which are, again, part of your body's immune system. I think if you've got AIDS, don't your T cells turn against you? That's kind of what the problem with AIDS is. Well, T cells are normally good because what they do is they go after bad viruses and eat them, right? They essentially eat them. And so it's producing them. So it's stage 1 and stage 2 are really good. Now, stage 3 is what they're doing. Stage 3 is where you take big, huge chunks of people and you'll do a double-blind experiment. So half of the people who are volunteers, and they're all volunteers, are going to get this drug, a vaccination. And the other half, I'm not sure if they're going to do a real placebo, which means that they just get saline solution, or they get whatever else is out there, as a comparison. And then they'll be collecting data on what percentage of each group caught COVID-19, what percentage of each group, how long it took them to recover, and how many of each group died. And if the data comes out good, and there's no guarantees because it might not, but if the data comes out good on that, they'll be straight into phase 4, which phase 4 is the factories start producing it and you go to Walmart and you get your injection. So that's what we're hoping for. It might fail in phase 3. You know, everything's good, and then, you know, it's not that very good, right? It's not a very effective means, and it might be. Be really cool if it was. Okay, I'm going to go now and look at some homework questions to make sure that I've covered all the good stuff. And I'm having to be really and the reason why I want to be really careful is that I'm tired. I've been grading, I've been doing 2 classes, and then I graded for 3 hours. And then I had to have a nap because I was exhausted. And the last class, I accidentally closed the Zoom meeting because I'm opening and closing lots of windows. And thankfully, it was in the last 5 minutes of the class. So I just kind of, people would be listening to me right now, right? And then boom, I was gone. So I'm being really careful. If by chance, because it could happen tonight, because it's 3 hours and so many minutes, I do that, we are all going to Zoom out of Zoom. I will be sending you a new Zoom meeting for you all to join back in again, right? So I'm telling you the get out of jail free card, right? That's how that's going to happen. I have no intention of doing it, but if I accidentally close the Zoom meeting, you will wait a few minutes for me to recreate a new meeting. I'll send you it the usual way, right, with a usual link, and you'll get back in. So you'll get like an extra 10-minute break that you weren't expecting. Okay. So back to what I was doing, which is this guy. Got these windows all over the place. Let's do a view on it. Okay, I have to go out again for a second and back in. And this is 6.3 that you're looking at. So it's up and running. Good. Okay, let's look at question 2, because this is the only version of is this thing normal or not? Okay, so can you imagine that this was the data that I collected, right? And these are people's ages, right, for whatever. Now, if you take this data, can you see that they've made, I don't like their histograms, but you can see they've made a histogram of it. If you look at that histogram, does that look normal to you? Well, it's kind of hard to tell, especially the fact that real data has funny bumps in it. They've drawn the curve through it. You know, I would disagree with the position of that curve. To me, shouldn't it be shifted a little bit to the left? But, you know, does it look normal? Well, the curve certainly looks kind of normal, doesn't it? I'm not convinced about the histogram. Might be, might not. So let's go over here. Here are the Z-scores, and here are the real scores. Do you see the plot that I was talking about? Would you agree that that plot is pretty linear? You don't get perfect, but it's definitely more straight than it is curved. Would you agree that much? So that means to me that this data is good to go. I can find its mean and standard deviation, and then I can start doing them, you know, bigger than 27, less than 42, in the betweens, and any other analysis I want to do. And I'm going to come up with pretty accurate results. So that's good news. We cool with that? It's only one question you got. You don't even make the table, right? But that's what it would look like if you did. And it would be software that would do it for you anyway. Now, I don't like this color scheme, but if you look really carefully, can you see that you've got Q1 and Q2 and mean and standard deviation, a few other things you don't care about right now, right? Oh, okay. Here are the answers. Let's talk about why they are the answer. Does the histogram indicate normality? And they have said yes. We observed a bell-shaped symmetric curve. I think you're pushing it, but okay, yes, I'll do. They're more generous than I would be. Does the normal quantile plot, which is this fella, does that indicate that you've got good normal data? Yes, it does. Would you agree that they fall pretty much on a straight line? So that one I'm happy with, right? That one I wouldn't argue with. Now, it says, what's the interquartile range? So if you go back to this data, how do you calculate interquartile range?
Isn't it Q3 minus Q1?
Correct. And isn't Q3 very faintly called 31? I hate this colour scheme. And isn't Q1 called 29? And take them away, and can you see that the answer is 2? Agreed? And check for outliers. Well, I'm going to do an eyeball here. Would you agree that 34 is not an outlier and 27 is not an outlier? Would you agree just by looking at the data, they don't look particularly bad? So you can figure out the rest yourself. Now, this one's a worked example only because I've got solutions. So let's take them out because they're beginning to distract us. Right. Okay, question 1. Consider a normal distribution with a mean of 21 and a standard deviation of 10. What's the probability? Another way of saying, what percentage of people have a score greater than 21? Wait a minute, isn't that half the people? And isn't that 50%? When they answer most of these questions, they want the answer to be left as a decimal. So 0.5 would be what you type in. But that is 50%. What? Why is the solution still there? Go away. There, go away. Go away. That's weird. Okay. Do you know these questions that I'm pointing at? That's questions 3, 4, 5, 6. Aren't they the normal CDF that we did at the start of today? Now, if you look at the question, isn't everything you need to know is here? 13.2 mean, standard deviation 3.7. The fact that they're using mu and sigma, doesn't that mean it's a population question? The population mean is 3.2 and the population standard deviation is 3.7, right? But it's still mean and standard deviation nonetheless. And you want to find a between, a bigger than, should be a less than somewhere around. Probably coming up on it. Are you comfortable about normal CDFs and how that would work? Right. In question 7, they've gone and returned back in 7 and 8, they've gone and returned back to Z-scores. Because isn't Z-scores just a special case of what we've been doing? Aren't Z-scores just a mean of 0 and a standard deviation of 1? Good. Right. Let's suppose we have an issue. I imagine that I have a test with a mean of 50 and a standard deviation of 15. And I'll draw my little visual picture as we very often do. I won't put all the numbers in. You could imagine what these numbers are, right? 1, 2, 3 standard deviations, right? If you are told that you got a score and it's the 82nd percentile. Oops, sorry. A little wobbly there. What you're looking for is what score, and I'm making a guess, it's about here. Right, what's your X value? So that 82% of the cake is over here. So if you're in the 90th percentile, suppose you get your SAT scores and you were in the 90th percentile, wouldn't that be a good place to be? Wouldn't that mean that only 10% of Americans did better in the SATs than you, and you did better than the other 90%, right? It's a kind of way of measuring how far along the spectrum you are in how well you did, right? So the question becomes, how do we find X? Well, I guess, couldn't I just keep guessing? Couldn't I say everything less than 60 and find out what percentage of people that was, right? So I could go and I could find out what that answer is. And I'm making this up. Can we pretend it's 73%? Well, that's not 82, so I know it's not the number 60. So I try the number 75, but that ends up being 91%. Do you know that game where it's too big, it's too low? Can't you just keep guessing until eventually you got a number that popped out with 82%? Not a very practical way of doing it, is it? Wouldn't it be nice if there was a button feature on your TI-84 that did exactly that job? Wouldn't it be nice if that existed? And the answer is yes, it exists. So let me show you who this button is. He is called the inverse norm. And he has a particular form. Here you put the decimal, in this case 0.82. Here you put the mean, which in this case is 50, and here you put the standard deviation, which in this case is 15. And what the calculator will do is it will find this guy for you. Now, since this standard deviation is 15, won't this guy be 65? Won't this guy be 80? And won't this guy be 95? So can you imagine that the number we're looking for is somewhere between here, roughly? Does that make sense? So you always use percentiles, and percentiles are what value has 82% of the data to the left of it. It always returns the number that has that percentage to the left. That's just the way it's designed. And let's show you what that looks like on the calculators. I almost closed this class by accident while I was doing that stuff. So I had so many windows open I couldn't even flip and find things. All I'm doing now is setting up the calculators because I ended up having to close as many windows as I could find just so we could, so I could work on getting your grades done. Okay, clearing this fella up, and I should be ready to share. And here we go. You know, if I have money, I'm going to get 3 monitors. So I can have one monitor with you, one monitor with what the screen is showing, and a third monitor where I can go in and out and do my file stuff. Do you think my wife would fall for that?
I mean, you have our endorsement, so if you need us to write you a note, I mean, we can do that for you.
What you really should do is write a note to my dean, my boss, and tell him that I need one because it's interfering with your education. And he will ignore you, but at least we tried.
You get a COVID grant for it. There you go. It's necessary.
There's a thing called a COVID grant?
I'm not sure if it's called that, but I've heard that there's money available.
That does remind me, CARES grant, C-A-R-E-S. Go online, Olympic, have a look, you know, apply for it, whatever it's called. Right, it's free money, use it. So anybody who hasn't heard about C-A-R-E-S, the CARES grant, go to Olympic College's site, type in that word, it'll put you to the application page and fill in the application and go for it. If you do have financial hardships, as I'm sure some of you do, you might want to contact Wish. I think it's called Wish, isn't it? Is it called Wish? No, darn it, I've forgotten the right name of it. But there's another place within OC that will help you. They can help you with little things, especially, you know, like a textbook or some money to buy something. They're not big grant people, but they sometimes have little bits of money. They use it up pretty quickly. Okay, back to this guy. We want to find what the score you would need to be in the 82nd percentile, right? So if you do it on this calculator here, where do you think it's going to be? Just curious. You haven't seen where it is, but where do you think it might be?
Stat.
Okay, so it might be in here somewhere. Yeah, could have been. Let's do second distribution. Can you see it's number 3? It was right under number 2, right? So it's in the same place that you've been doing a lot of. So I'm going to scroll down to inverse norm, and that's what it looks like here. And the guy that they call area is the 82% written as a decimal. The mean in this question was 50. And the standard deviation in this question was 15. And just to make my life simple, will you just keep it on left all the time? And then go down here and you hit paste. And so it'll look like this. Now I'm going to do it on this machine in case you've got an old one. If you do this guy, it's still number 3 and it was still in the same place. Here you have to type in with commas the same numbers. So 0.82, comma 50, comma 15. And it just automatically knows it's to the left so you don't tell it. So when I hit enter, you need to get in the test about what, 64 if you round it off to a whole number. And if I go over here and I hit enter, did I miss the enter button? Hit enter. Right, it works. So what does that tell me? It tells me my picture was really bad. But isn't the missing score that you would need to get to be in the top 82% would be a score of 64? Right. Cool. Now, let's, can you imagine you change that number? I could do that pretty quickly, actually. So if I wanted to keep everything the same, but I would like to know the 10th percentile, which isn't a very good score, isn't that you in the bottom 10% essentially? And you would end up, if you get what, about 31 in the test, would put you in the bottom 10%. What number, what decimal number should I use if I wanted to know what the person in the 99th percentile was? It's really not a trick question.
He's 99.
It's 99, right? So I can't guarantee this, but isn't that probably the guy who got the highest score? And by the way, guy is sexless to me. Girls are guys and boys are guys, right? So I'm getting that out there. And it does mean that, because I will say to people, you guys come with me, and half of them are girls. You know, or do you guys follow me? Whatever, things like that. Are we cool? New guy in town. Now, they could sneakily ask that last question a different way. The way I said it is, what score would you need to be to write to be in the top 99%? Right. Couldn't I ask it, what score would you need to be in the top 1%? Isn't the top 1% the same thing as the 99th percentile? What would the top 10%, because sometimes they phrase it as top something, right? What would the decimal be for the top 10% people?
0.9.
0.9. And the bottom 10%, wouldn't that still be 0.1? The bottom 10% is your percentile, right? But the top 10% is 90%, right? So there's a little calculation. Don't you basically take it away from 1? You know, the decimal away from 1. So 99% would be 0.99 away from 1, which is 0.01. We go with that? Right, let's see if we can use that in an example. I am going to go online, and you don't need to see this. And I am going to do a percentile question on some medical data. So all I need to know is what the mean and standard deviation is, right? So let's find out what the mean and, oops. The mean and standard deviation You know, I should have let one of you do this. I'm really bad at hitting buttons on my one finger typer. For, let's do blood pressure. That's one that I did with my other class. That worked out quite well. Who knows, I may not get the same data, but I have to trust the data. Oh, I did get different data. This is good. The medical people amongst you, the nursing, the thing they're telling me here, I'm writing it down, is called the no it isn't, try again, DIASTOLIC. Does that word mean something to you? You heard of the diastolic blood pressure?
Yeah, it's your blood pressure at rest, or it's your blood pressure when your heart is not contracting.
Okay, so
Your heart is rest.
right. According to oh, I was looking. Oh, darn it, I lost it. The one I was looking at wasn't actually. Okay, I think if I click on this one. Oh, shoot. Excuse the language. All I wanted to find was those two numbers. And what I'm getting are numbers for people who aren't well, which really isn't what I need. And the reason for that is that I didn't use Google.
Are you asking what normal blood pressure is?
Yes.
120/80.
Okay, so we'll take the 120 one, right? So is that the diastolic one, the 120?
Systolic is 120.
Okay,
diastolic.
let's use diastolic. So that's 80?
Yeah.
Right. So all I need to do now is find out what the standard deviation is for a typical population. And then I'll be ready for my questions that I wanted to do. I guess if I go into Google, somebody, is anybody good at finding things? I want to find the standard deviation for diastolic blood pressure. That's what I'm searching for. Standard deviation of systolic thingy blood pressure. Can't even say the word.
Okay, I've got it right here. It's
Perfect.
do you want for males or females?
Oh, I guess we should specify. Let's do it as males.
Okay, so for males, normal standard deviation for diastolic is 10.9.
That's the standard deviation?
Yeah.
Perfect. Okay. Now, can you imagine that any medical data has probably got stored somewhere, probably in a medical manual, you know, a book that you store things like this in, and it will tell you the mean potassium level and the standard deviation within a normal population. Males and females, they probably even have, for some of them, don't they have age groups, right? So I know when I get, because I am older, that they're a little bit more generous about what my blood pressure numbers are, because as you get older, the average number kind of changes a little bit, right? An 18-year-old's blood pressure is probably a little bit different from a 68-year-old adult, right? But whatever that is, 80 and 10.9. Are we looking at the right picture here? Because I don't know which one I've got open now. Right, here we go. Right, this is the guy, right? So I can use this to answer some questions. So, for instance, you know when you get your blood pressure, if it's really high, it's given a special name, isn't it? What do you call it when your blood pressure is really high?
Hypertension.
Hypertension? Okay. I'm making an executive decision. If you're in the top 10%, that means you're really high, right? You're in the top 10% of high blood pressures for people who are still alive, right? 10%. I would like to know what blood pressure that is. So if you can imagine a top 10%, isn't this guy over here 10%? But won't the number I be using is the 90th percentile? Agreed? So, inverse norm. 90%. 80 is the mean. 10.9 is the thing. And I'm just going to use my calculators for speed rather than going all this out and in stuff. So inverse norm, 90%, which is 0.9, comma, a mean of 80, comma, a standard deviation of 10.9, finish it off, and the answer I am getting is about 94. So see if your diastolic blood pressure is 94 or bigger. That makes you in the top 10%, doesn't it? Wouldn't that probably be diagnosed as you've got hypertension? Now, do you see where that number came from? So if you look at when doctors do tests and things, and you're a nurse, you're doing the normal checkup that I get. The woman always comes in and checks my blood pressure and all the other good things. Can you imagine that when they look at this, they'll look at that number, and I always say, what's my numbers like? And there are two answers to that. The one is, it's good. And the other answer is, wait until your doctor talks to you. That's not a good answer normally when they say that, but occasionally they do, unfortunately. Yeah. Do you know, if I was a horse, they would have shot me by now, the number of things that are wrong with me. They're just falling apart at the edges. But can you see where that number came from? Does anybody know what the opposite of a high blood pressure is called? Just out of curiosity.
Hypotension.
Oh, just a thingy. Have you taken that nursing program or biology program where you name parts of the body and you name things?
I would love to, because I do archaeology, and knowing what bones are what is really, really helpful. But no, I haven't taken that. I'd love to, though.
Has any of you taken that class? I think it's a biology class, and you just learn all the Latin and Greek names for your tibia and your
that's
aorta.
anatomy.
What's it called again?
Anatomy. You do
Right.
anatomy 1 and 2. I've taken those.
Right, so is these the kinds of terms that you've heard somewhere before because of that?
That's
Right.
like every science class.
Right, so whenever you're in the medical program or the medical world, they use a lot of Greek and Latin roots, don't they, in the naming of things. So if you know just a little bit of Latin or Greek, you can actually have a fighting chance of creating what the thing's probably called. Right, now back to this one. Let's suppose that you have to be in the bottom 10%, right? So that's the 10th percentile to be in hypotension. I wonder what the blood pressure for that is, because right in the middle it's 80, right? Well, let's see. That's going to be an inverse norm again, but this time 0.1. Now, I'm going to come up with this number, and you're going to tell me that if you know that this is a reasonable value for what is considered hypotension. So 0.1, comma 80, comma 10.9. And I am looking at about 66. So if you were taking someone's blood pressure and it was low as 66, would you be concerned with that number?
No, because 60 is technically, so 66 is getting there, but 60 is technically when they diagnose it as hypertension.
So I wonder if it's the bottom 5% then. See, basically you're in charge of what you want, right? So if I use this, wouldn't 10% of the population be diagnosed as hypotension? Because isn't that the score that would give you 10% of the people? Now, if I move the goalpost down to 5%, can you see that it could well be the number you just said? So you said 5%? I should be able to check that really quickly without really doing too much here. Although you can't see what I'm doing, I'm actually retyping the thing. And if you are in the 5% range, you are 62. So evidently, you have to be in a very small window less than 5%, right? But 5% is only 1 in 20 people, right? So I guess that's still kind of big, isn't it? 5% is 1 in 20. Does it seem to, the numbers are coming up with, can you see that they kind of match reality in what you would expect if you had a mean and standard deviation? And I can guarantee that whatever numbers they've decided is too big or too small, right? Too large or too small. They have created this kind of analysis that I've done. And there's a bit of subjectivism in here. I know, for instance, haven't they changed what they consider blood pressure numbers that you should be given medication to control?
I think they dropped it by 10 millimeters per score just recently.
Right. So yeah, that's what I was thinking. So I think what's happened here is that they've decided to err on the side of caution, because I get blood pressure medication. I used to not, and then they told me that, you know, maybe it's partly my age as well. They said, yeah, they've changed the standard or some phrase like that. And now if your number is this or higher, you now should be taking blood pressure medication. I think the reason for it is that the pills I take, this is not an exaggeration, a month's supply cost me 67 cents. I mean, it's went totally generic, I guess. Or if I just get really good insurance, I don't know which. But it's ridiculous.
They use like sawdust or something.
They're made out of sawdust, whatever. And since it's so cheap, and it probably has a lot of health benefits, you know, it's worth it. The insurance companies have probably said, yeah, we'll make it really cheap, because I'd rather pay for that pill than the heart attack and all the other nasty things that would happen if you maybe let something go for too long. So are we comfortable about how to do percentiles now? Right. Now, one special case. If it was a Z-score, wouldn't your numbers look like this? Okay. And couldn't you get the question that would say, find the Z-score to be in the 82nd percentile? So somewhere over here, I'm guessing, right? Well, it's actually an inverse norm. In fact, isn't it just a special case? If you want 82%, isn't 82 percentile 0.82? What do I put for the other two numbers, because it's a Z-score?
That one's going to be 0.
And 1. So isn't the Z-score question just a special case of what we've already been doing? We comfortable with that idea? So they might say, what Z-score is the 80th percentile, right? What Z-score puts you in the top 10%? What Z-score puts you in the bottom 20%? You know, questions that are like that, right? The same kind of questions that you get with IQ tests or with hypertension. You know, what score would you need to be in the top 10% of blood pressure, right? And so on. We feel comfortable about the Z is just a special case of what we're already doing. So I'm now going to return to the homework questions, and we'll look at some more of them. With a bit of luck. Darn it. Let's try that again. I'm going to need a joke in a few minutes, because I can tell my focus is going. Oh, you don't want to see that. That would have been your class grades. Should have closed that window. Never mind. I believe it's this one. Looking good. Right. I'm almost ready to show you. Right. Okay. Stop and then go back in, and it should be here. Find the z-score such that your 5% of the standard normal curve lies to the left. Isn't that a fancy way of saying find the 5th percentile? Now, in this picture here, if 5% is to the left of z, isn't it this picture here, the second one? And up here, won't you do an inverse norm? And you want 5%, so 0.05, comma 0, which is the mean, comma 1. Okay, there wasn't a lot written, but can you see that's what the calculation that would do that? Can you imagine doing this question would probably take you less than a minute, because it's virtually all calculator, isn't it? And then answer to 3 decimal places. Do you notice that they want not 18 or 18.123 4. They want 18.123, right? They want 3 decimal places, which is fine because that should be what your calculator gives you. Now, find a z such that 72% of the curve lies to the left. Which one of these pictures looks like 72% of it lies to the left of it? So that's picture 1, 2, 3, and 4. Which one of them has 72%?
Wouldn't it be the bottom right one?
It would. 72% to the left. If I did 0 to the left, wouldn't that be 50? So can you imagine this is just a little bit more than 50? Up here, when you do an inverse norm with 0.72, there's another one just like it. Oh, here's one to the right. Find a z, right? So find out what the z-score would be if 6% was to the right. Well, if you want 6% to the right, isn't it this one? Would you agree that little piece is 6% based on the choices? That's the best candidate at least, right? If I'm doing my inverse norm, I won't use 0.06 then, will I? I will use 0.94, right? Take 6 away for 100%, right? 0.94. And there's a similar question. And then, I know this book jumps about a little bit, which is annoying, but that's what it is. Here we're back to inverse norms, right? What we did at the start of today, right? Not inverse norms, sorry. Normal CDFs, right? We're back to normal CDFs now, right? Bigger than 60, less than 110, and the between stories. Now, won't that be a normal CDF question? Same idea, 12-volt batteries, and so on and so forth. Question 17 and question 18 are kind of interesting because what they give you is a calculation here, and it basically is a very, very crude way of looking at data and guesstimating what the standard deviation would be. If you are a normal distribution, the range divided by 4, which is the biggest number, take away the smallest number divided by 4, is roughly going to be the standard deviation. Do you know where the 4 comes from? Why it's not 6 or 8 or 2? Right. Well, those 2 questions you're basically going to read over and do, so let me show you where the 4 comes from instead. If you do a normal standard deviation, right in the middle is the mean. Could be anything, right? If you go 1 standard deviation, it's written like this. Can you remember 2 standard deviations? It looks like that. If you go 1 to the left here, you take away 1, and then you go 2 to the left, you take away 2. So far, so good, right? Now, I've only done 2 standard deviations, right? Now, between here and here, It's not all the data, but isn't it 95% of the data? Right, 2 standard deviations. So what they're saying here is, kind of sort of 95% is kind of most of the numbers, right? And if you go from here to here, isn't that 1, 2, 3, 4 standard deviations? And if you think that these numbers are really pretty close to what the small and the big is, which we call the range, then won't 4 standard deviations be very roughly the same as the range? So won't a standard deviation be the range divided by 4? So there are a couple of little questions where you play about with that. And I don't want to do everything for you. I think it's cool to just learn stuff on your own as well. And so I'm going to just return to that, and let's look at, okay, I'll pick one question. This is the last one, question 20. And I'll get the details here. Most exhibition shows open in the morning and close in the late evening. True. A study of Saturday arrival times showed that the average arrival time was 3 hours and 40 minutes after the doors opened. Okay, so mean is 3 hours and 48 minutes. I'm going to have to fix that, but I'll write it down right now. And the standard deviation was 54 minutes. Okay. At what time after the doors open will 87 of the people who are going to come have already arrived? So I'm now going to do that 87% thing. And this is an inverse norm question. It's just the way it's phrased might throw you a little bit. So let me try and put that into context and show you what's going on here. I do not like mixing and matching units. You can't really do 3 hours and 48 minutes. So what I'm going to do is do 3 times 60. God, that's slow. And then I'm going to add 48. So the mean is 228 minutes after it started. So, you know, the doors might open at 7 a.m., but, you know, most people don't turn up, you know, until 10 a.m., right? That kind of thing. And the standard deviation is 54 minutes. Now, can you see why I chose to convert the 2 datas into the same units, in this case, minutes? Because I like whole numbers. If I had to, couldn't I convert that data into decimal hours? Right, so that where, for instance, would be 48 out of 60. That would be 3.8 hours, and that would be an ugly number. Right. Now, imagine your distribution, 228, and the standard deviation happens to be 54, and you are trying to find the score, the number that goes here, so that 87% of the people have arrived. Well, that tells me it's an inverse norm question. It's everybody to the left, so that means I don't need to change anything, right? I can use 0.87, the decimal version. Won't the mean be 228 and the standard deviation will be 54? And then I'll go to my calculator and I'll find out what the heck that is. So second distribution, inverse norm, and 0.87, 228, 54. And I am looking at about 289. I've decided to make it a nice round number. So 289 minutes after the doors are open, 87% of the people who are going to arrive have arrived, right? So you haven't got everybody, but you've got 87%. I guess if you are being a purist, that would be 4 hours. And 49 minutes. So if the doors open at, say, 7 a.m. in the morning, almost noon, right, 11:49, 87% of the people have arrived. So you can imagine that if you're time management and you're looking at things, you would probably tell the people who are running the conference that if you want to get the greatest number of people to pay attention, you probably shouldn't do your main presentation to after lunchtime or something, when almost everybody who's going to be there is there. Don't do your major presentation at 8 a.m. in the morning, because can you imagine if you did it at 8 a.m., only 10% of the people are there, so you're kind of talking to an empty hall, for instance. So I'm just making up why you would want to know that kind of information. Right? Are we cool with what an inverse norm question might look like? It might simply be a story like this one, where you create a picture and then recognize that you're being asked to find a particular value of X that represents a percentage happening. Are we good? Right, I can tell my brain is getting a little bit fuzzy, and we still have a lot to do. So to give my brain a chance, I'm going to give you 5 minutes this time. So why don't you have a little 5-minute Pepsi, coffee, whiskey, no whiskey, not allowed. Pepsi, coffee, or whatever it is. I have to drink this bloody water. Because evidently the stuff I used to drink was bad for me, and my doctor told me I've not to drink it anymore. Have you noticed doctors always tell you to give up stuff you like and tell you to do stuff you don't like? Like eat lots of carrot and lettuce and stop eating steak.
Just a bunch of sadists.
They are. You know, if God wanted me to be a vegetarian, he wouldn't make steak taste so good. Right? And I have never, to this day, I've never met a happy vegan. They always look sad. In my
No, they always
opinion.
want they want you to know about it too. I mean, they can't. They're not happy. They're not content. They want everyone else to suffer just as much as them.
Yeah. That's not nice, is it?
No, it's not.
Cool. Yeah. Well, I come from Scotland. Scottish food is ridiculously bad for you. It's like the south of America. I believe in the south, if it moves, you fry it. Right? Everything gets fried, right? Even the cakes get fried, I guess. You know, stick batter around it and it gets fried. Same thing in Scotland. They fry everything. We have a chocolate bar called a Mars bar. I don't know if you've heard of it. M-A-R-S. It's a Mars
They
bar.
have them here. They just started selling them. I've seen them in stores. They're nothing alike, but that's what they're calling them.
Okay. They're basically pure chocolate stroke sugar. I mean, definitely not bad for you. Horrible for you, yes, but not bad for you. So what they do in Scotland is they wrap it. You go into a fish and chip shop, they wrap it in batter and they deep fry it for you.
Why?
I don't know why, but that's what they do. I mean, they're literally, if you go into a fish and chip shop, you'd be amazed at what can be fried. Do you know a sausage? Just a normal big sausage, right? Like a German shaped sausage, right? They cover it in batter and they fry it.
I can understand that a little bit more than a deep fried Mars bar. That just doesn't make sense to me. Although that does sound like, if you would have told me that, I would have guessed it was American. Like that sounds like the South to me.
Well, I wonder if the South got a lot of Scottish influence. Did a lot of Scottish immigrants maybe go south rather than north? I don't know the history of America, so I'm just putting that out there. Is there anything like that? Or is it? Just
Yeah,
we
I
had
thought
a
it
strong
was-
influence, maybe.
Yeah, no, I thought it was just the a bunch of Scandinavians that went down that way that filtered down from what is it, Wisconsin?
Okay.
I don't know.
I don't think Scandinavians are famous for frying things.
I think quite the opposite.
Yeah, I'm picturing Scandinavians as, you know, where's my rucksack and they climb mountains all the time. Is that a bad stereotype?
No, I think they probably like it. And that's probably the opinion they want people to have of them.
Never been to Scandinavia. It's not on my bucket list. I mean, I'm only going to be on this earth for a certain amount of time, and there's lots of places I could go to, but to be practical about it, there's only a certain number of places I will ever get to go. And so it's not on my hit list. Russia is not on my hit list either. I don't feel any great need to go to Russia. But if I went to Russia, they'd probably arrest me because I don't like their politics. And they tend to frown upon people that don't agree with them, even if you're a foreigner.
Oh, I've heard of people getting turned away at the airport if they just don't like the look of you. They say go home, like we don't want you here.
Yeah, you look like you've probably got a independent thought in your head, and we don't like those kind of people. Yeah, they'd probably kick me out if they knew what my opinion of their politics were.
Well, honestly,
I
it's
don't-
probably a compliment. You know, if you're welcomed with open arms, you know there's something wrong with your reasoning.
Some of your politicians are, strangely enough, which is kind of worrying, but that's a different story. Russia, I've mentioned. China's not on my hit list. I don't want to go to China. I want to go to Thailand. It's not I've got anything against Asia. I think Chinese people are lovely people, like everybody is pretty lovely. I'm a bit dubious about the French, but apart from them, everybody else is pretty much nice, at least the ones I've met. But, you know, I like Thailand because my niece went to Thailand. She done a really cool thing. She had a long-term relationship with her boyfriend, and he cheated on her when they were talking about buying houses and getting married, right? They were at that really serious stage of the relationship. And so she quit her job. She had a great job. She quit her job and she spent a year touring the world. And it was a great therapy for her. And one of the places she went to, which is why I like Thailand, is she went to Thailand and you can go on elephants there. You climb on elephants' back. And I don't know why elephants, it just looks so cool. She had a video of it and I thought, I want to do that. Now she'd done some other stupid things in my opinion. She bungee jumped to New Zealand. There is no way you're attaching an elastic band to my waist and chucking me over the side of the bridge. It ain't happening, right? That is not on my list. But elephants, I could do that. What else did she do? Snorkel dived in the Barrier Reef in Australia. And she did, do you know that tandem parachute thing where you get attached to a guy who knows what he's doing and he jumps out of a plane?
Mm-hmm.
She did that. I mean, she just basically did anything she felt like. She did a great job. She had plenty of money in the bank to do it. And then she ended up in Australia at the end of it. And she got a work visa because her job is so good. She's so good at her job. And she worked there for 2 years and then got homesick and came back home and she lives here now. And the guy that cheated on her got married to the person he cheated on. Because people, you know about people because you live in the same area, you're bound to find out. And he cheated on her and got divorced. So she lucked out there. Right? She could have got married and then he would have cheated on her, right? Because, you know, people who do that typically, it just means he got caught. That's what it means to me, right? He just got caught. I'm sure he cheated on her more than that one time, right? And some guys are like that. So she did well.
I'd choose jumping off the bridge in New Zealand to that.
You would do the bungee jump?
Oh, compared to this guy, yeah, if those are my two choices, I'll take the bridge. Thank you very much.
Oh, okay. I guess if you do it that way, yeah.
I think there's probably more options out there than that, but given those
I
two-
think there is more options than bungee jumping or staying with a partner that you don't like. But who knows? Okay, I've had a little break, a good chat. It gets my brain moving. So where are we off to next? Well, the next section is really quick. There's only, I think, pardon me, 8 questions in it. So to make your homework a little bit easier and to actually, it gives me a good teaching opportunity. We're going to do those questions together for the most part. And so we're going to look at section 6.4, which is called sampling distributions. And I was right, there are only 8 questions. So you'll see it in a few seconds. And I've got the key with the answers on, because it's easier if I just tell you the answers and then I explain why what it is the answer. Because it's really just an intro to something. The last section, which is on that we're going to focus on right after this, is the bread and butter one, right, where all the good stuff happens. So let's get this guy sorted out. I think it's that one. Yeah, we're looking at it. Right, so which of the following are examples of populations? Right, now a population is just a whole group of people or things, right? So antelope in Wyoming is a population. Can you imagine you were interested in the weights and height and whatever, how many, you know, stuff to do with antelopes in Wyoming? Wouldn't the population be antelopes in Wyoming? Students in our school, could that be a population? Yeah. In fact, I've used quite a few questions that are based on assuming that we're interested in just students at OC. And people in Colorado, that would be a population. So you might say, well, what is wrong with the other two? Well, aren't the other two numbers, not populations? The percentage of people own a car, isn't that just a single number, 82%, 47%? In fact, don't we call those things statistics or parameters, depending on where the number came from? If I got 20 people and I found out how many of them owned a car, wouldn't that percentage be a statistic because it came from a sample of 20 people? If I found every single person of America and I asked them the same question and I got 39%, wouldn't that be called a parameter? So isn't a parameter a number that you got from a population, and a statistic is a number that you got from a sample? Does that make sense? The distinction between what you call that. Now in this case here, proportion or percentage, you know those words are pretty much interchangeable. Percentage is 42%, proportion is 0.42. Isn't it just the way you write the number? It's not the thing is different. So they're both numbers. Now, question 2. I mean, it's going back, way back. Can you remember doing simple random samples and what they were? And it says here, a simple random sample of n measurements from a population is a subset of the population selected in a manner such that which of the following is true in a select order apply. I mean, I could have they've made a meal of that. Couldn't they just say, which of these things describes a simple random sample? That's what they're asking. So the first one, every member of the population has an equal chance of being included in the sample. In fact, isn't that pretty much the dictionary description of it? So I would hope you pick that one. Now, the next one that's correct is every sample of size n from the population has an equal chance of being selected. So if I did a sample of 100 and you looked at every single possible sample of 100 that you could ever get, in a simple random sample, wouldn't every single one of those samples be just as likely to be the one I picked than any of the other samples of 100? So that is a weird version of a simple random sample. Right, what is a population parameter? Well, here it goes. A population parameter is a numerical, means a number, description that measures, that describes something to do with a population. So isn't a parameter a number that tells you something about the population? So a parameter could be the mean of the population, the standard deviation of the population, and the percentage of people who are going to vote Democrat. Couldn't that also be considered a parameter? We have letters of the alphabet that are used for those kinds of things. 2 we know and 1 is new. Do you recognize that guy there that's called mu? Isn't that a parameter of a population? Isn't that the mean? The other one that we know, do you see that top one there that's got a little key, so that's the right answer? Isn't that sigma, which is what, the standard deviation of a population? Now, do you see the one that's new? It's called P. Can you imagine a question, we haven't done any yet, but we will eventually. Can you imagine a question where you ask Americans their opinion on something and 42% say yes? That's what P is, 42%. So 42% are going to vote Democrat, right? 59% of people like sci-fi movies, right? 2% of the population believe politicians tell the truth, right? Whatever it is. Those are the kind of P's that you got in the world. Now, in question 4, they just change it on its head. Isn't a statistic a number that describes something to do with a sample? And X bar is 1. S, well, I'd call that ST, but isn't that the standard deviation? So that's 1. Do you know this new guy, P hat, the little hat at the top? It's called P hat. Right? That's what you say out loud. Do you know that is, you get a sample of 200 people and you say, how many of you are going to vote Democrat? And 53% said we're going to do it. P hat would be 53% in that case. So P hat is the name that we use for a sample. P is what you'd use if you ask the same thing of the entire population, right? So P is a population parameter. P hat is a sample statistic. Oh, does anybody know what S squared is? Because I don't even think we did much on that, if anything. It starts with the letter V. You might have seen it somewhere.
Variance.
It's called the variance. Its name tells you what you do. Don't you take the standard deviation and just square it? You know, so if the standard deviation was 4, variance would be 16. It's a less used measure of how spread out data is. Yeah. Now, the meaning of the term statistical inference. You collect data and then you make, we did some of it today, didn't we, for instance, come up with things like what kind of blood pressure number you would need in order to be a really high blood pressure, you know, that kind of thing. Or, for example, or what IQ score you would need to be in the bottom 10%, right, things like that. Well, a statistical inference is what that is, right? You're collecting data and then you're making some calculations based on it and coming up with a conclusion. So it's a conclusion about a population parameter based on the sample statistic. And estimating and testing, right? Estimating. If I collect a sample of 200 people and I use it to predict the age of Americans, haven't I used an estimate in that case? My sample mean is an estimate of what the population mean is probably going to be. Does that seem reasonable? That was an estimate. Testing. Couldn't we use testing to test what kind of blood pressure would be considered really high? Right? What kind of blood pressure number do you need to be in the top 5%? Suppose we say that you're a genius if your IQ is in the top 1%. Aren't we doing a test there? What number do you need to be in the top 1%? So that's like an inverse norm. And then they go on and they do a couple of questions, which I'm going to skip by because they're going to be covered in my next intro. We are essentially on to the final section. And it is 2, 3, 4, 6, 5. And it is, we're going to deal with this called the sampling distribution. And I'll need to spend a little bit of time giving you the intro behind this. Imagine that I was interested in the average age of Americans. And we'll say it's average age of American adults, right? So in this case, let's say the population is only people 18 or over, right? So for whatever reason, I'm not interested in the others. Do you get to vote at 18? Is that the voting age in America? You're 18 or more, right? Okay. So maybe we want to know this because we want to know the average age of American voters, right? So there's going to be a little newspaper article that says the average age of American voters is 47 or 29 or whatever it ends up being. Now, the typical way that I could do that is, couldn't I find every American adult and find their age and get the population mean? Isn't there a really big practical drawback to that technique? Have you any idea how much money it would cost to find every single American and pay people to go and ask them their age? I mean, can you just think just the sheer, organization that you would need to be able to do that? And do you know the only people in the world who do those kind of questions are governments? And just by coincidence, isn't the government doing a census right now? Now, a census is a fancy word for we ask everybody. Technically, they never get to ask everybody. Aren't there some people that you never get to ask? Right? They don't have a home address. They moved 2 days before the letter arrived, right? So they don't even get the letter, right? But in general, you can probably find that a census will get more than 90% of the population, right? They'll get to see at least that. And do you know why they use the census? It's used for a lot of purposes. And why would the government spend a lot of time and money on collecting that kind of data? Any ideas why they want it? Well, how about this? Don't they need to collect data to know the size of every county in America and the size of every state in America? Because a lot of funding is, federal funding is based on how big you are. Do you know that Alaska gets a certain amount of money to do schools and to do roads and things through the government grant process? Wouldn't you expect Texas to get more money than Hawaii? And it's not that they like Texas more than Hawaii, but doesn't Texas have a lot of people and Hawaii doesn't, relatively speaking? Well, how do you know that? Well, the only reason you know it is because you did a census, right? You counted people. Isn't that essentially what your census used to be? They just wanted to count how many Americans there were. And then they slowly started asking, I believe, do they now ask you your age on the census? Am I the only one who got a census form? Because that's scary if I did. Do they ask you your age in a census form? Or is it your mum and dad that does it so you don't care? Okay, it's your mum and dad that does. Courtney, you probably stay in your house. Do you know anything about the census? What did they ask?
In a while, but I think they ask your age.
Okay, so they're the only people that could do that. Let's suppose we haven't got that kind of money. So back to this story. What could I do? Well, couldn't I collect a sample? Well, yeah, we could. And let's suppose my sample was 1,000 people. And I got the mean of that sample. And it ended up being 35. Now, let's pretend that I actually know the right answer because I got the government data, right? I got the census data. And I know, because they do it by computer, that the real answer was 34. Just for argument's sake, right? Is it a surprise to you that my sample didn't agree with the real answer to the entire population? Not really. Isn't a sample going to be a little bit off? It's bound to be, right? Sometimes you get a few extra people a little bit older, sometimes you get a few people a little bit younger, right? But shouldn't that number be pretty close to the real number? Now imagine Bill Gates gave me a lot of money and he says, you can do as many samples as you want. So I'm going to call this one N1 X bar 1. So I decide, because he's given me the money, to ask another 1,000 people, a different 1,000, and I get their age, and I'm going to call it X bar 2. So here is my next question. Do you think that this mean will be exactly the same answer as the first sample? No, there's no reason. Oh, do you think my second mean is going to be 34? Probably not. Probably pretty close to it, right? But not necessarily. So can you imagine that my second sample might be 34.2? Now, can you imagine that I had an unlimited amount of money and I decided, because Bill Gates is paying for it, to do 200 samples of 1,000. God, that would cost millions, wouldn't it? But I did it because he paid for it. And the last time I did it, now occasionally, especially if you round off, won't I get some answers that will be the same? That seem reasonable. Let's suppose the last one was 33.8, just for argument's sake. What I now have is a rather interesting set of data. It consists of the means that we got from 200 samples. Now, can you imagine these 200 different numbers, what they might look like? What kind of shape do you think, if I put this into a histogram, what kind of shape do you think you might get? And by the way, the name of that shape is called the sampling distribution. Well, I get this shape. This is kind of weird. The average of all these means would be 34. It would end up being the population mean, or darn close to it. The standard deviation of this population, right? So in this case, this is the population. The mean is 34, and can I just tell you that the standard deviation is 10, right? The sampling distribution, it has a mean of the same number, but it has a different standard deviation. And the reason it has a different standard deviation is because you're averaging over 1,000 people. So its standard deviation is sigma over the square root of n. So what does that look like? Well, it's a very narrow distribution. Almost every single time you do a sample, the answer you get will be pretty close to 34. Would that make sense? Okay? Pretty close. Now, the n that I'm talking about, it's not the 200 times I did my sample directly, it's the 1,000 people in my sample. So, in this case, it would be 10 over the square root of 1,000. N is the size of one sample. And some really clever person figured out what that standard deviation looked like. And we can use this result to not only estimate by using one sample. So although the theory says you do it lots and lots of time. In practice, you only do it once, right? You do one sample. But what it allows us to do is it allows us to look at our sample and put an estimate, a tolerance around it. Okay, let's imagine then that I collected data and it was 100 students, and the average age of the 100 students is 28, right? And the standard deviation, will just be told, was 5, right? Just for argument's sake. I can use my sample of 100 to predict the population mean, right? Everybody in America of a sample of 100. So let's see what my prediction for the population mean would be. Well, I'd use 28, great. Now, if you imagine that's what my distribution looks like, if I had to pick a number, wouldn't I pick that one as my best guess at what the mean would be? Now, what's the standard deviation going to look like? Well, it's going to be sigma over the square root of n. It's going to be 5 over the square root of 100. It's going to be 0.5. So 28.5, 29, 29.5. And if I go this way, 27.5, 27, and finally 26.5. Essentially, I have a normal distribution. What percentage of the data is between here and here? That's 3 standard deviations either side of the mean. What percentage of that data is in that range?
99.7.
Right. So I could say this. This is my conjecture, I am 99.7% confident that the true mean age of Americans is somewhere between 26.8 and 20. What's that, 5? That's a 5. 26.5 and 29.5. I could write it down in the equivalent form. Isn't it 28 plus or minus 1.5? So what that allows me to do is from one sample, just a single sample of 100 people, that's my best guesstimate of what the population mean is. It's 28, give or take 1.5. So it might be as low as 26.5, it might be as high as 29.5, but I'm 99.7% confident that it's probably in that range. That's quite powerful. Doesn't it give you some idea of where the real answer lives? If I just said my sample had a mean of 28, and I told you nothing else, you see that's only part of the information. It doesn't really give you a good idea of what it's like. Imagine I told you this. It's 28, give or take 1.5 years, or it's 28, give or take 10 years. This fella is anywhere between 26.5 and 29.5, and this guy is anywhere near. Would you agree that the first one is telling me more useful information than the second one is? In the sense that I'm pretty sure I know where the mean is. Would you agree here the mean could be anything? Right, the population mean could be 18, it could be 38, it could be any number in between it. Wouldn't I be better just guessing? 28, yeah, call it good. We are not ever going to be doing 100% confidence. That's not the way statistics works. We can be 90% confident, we can be 95%, we can be 99%, whatever you want. We can be those numbers, but we can't be 100, except in one special silly situation. Suppose I'm measuring, say something like the percentage of Americans who are going to vote Democrat in the next election. Suppose I told you the answer was 50%, just for argument's sake. Suppose I now tell you it's give or take 50%. Would you agree that I am pretty guaranteed to have got the right answer? Somewhere between nobody in America votes for them till every single person in America votes for them. Would you agree that interval is 100% guaranteed to pick the correct answer to what percentage of Americans are going to vote Democrat? Would you also agree that interval is totally useless? It tells me nothing useful. So that might be what you got. That might be what you've got. It depends on the standard deviation, the sigma over root n. If your sample size is really big, because the standard deviation is formed by this calculation, and n is the sample size, can you see what happens to this number? Because the top's always, whatever it is, say 10, right? That's not going to change. But can't the sample size change? Can't you ask 2,000 people, or 2 million people, or 20 people? But what happens to the value of this when n is really big? Doesn't this become really small? And if this becomes really small, won't the plus or minus 3 standard deviations become tiny? So if I did a sample of 1 million Americans, do you know I'd be able to tell you the mean to about 2 decimal places, no matter what I asked them? Because isn't 1 million people a really big number? And that means the plus or minus is going to be tiny, right? Plus or minus and say 3. Very powerful technique. That is how we analyze our samples. We don't just find the mean, we find this guy. It's called the central limit theorem, is another name for it. Any questions about that? I know it's been a long day. You still with me?
Can you walk us through each part of the equation again real quickly?
Yes, I'll do another example then, that way we can start from scratch, right? So let's suppose I did a sample of 10,000 people. That's a big sample, right? And I wanted to know, oh God, I need something that I haven't talked about. I wanted to know what the average height of them were, right? And the average height I got was 65. And in the question, you're going to be told sigma. So let's suppose that sigma was 10, just for argument's sake, right? Now, when you do this question and you want to create my little picture that looks like this, right? The sampling distribution picture. Let's see what we can do. My mean is 65, so that goes here. According to the formula, the standard deviation of this distribution, it's called the sampling distribution, is sigma over the square root of n, which is 10 divided by the square root of 10,000, which is 10 over 100, which is a nice, easy to calculate 0.1. Now, 1 standard deviation, 2 standard deviations, 3 standard deviations in both directions. So won't this guy be 65.1, this guy will be 65.2, and this guy will be 65.3, and going backwards, 64.9, 64.8, and 64.7. Now, there's a lot of questions you can now do with this, because I know everything I need to know, right? It's normally distributed. Isn't its mean 65? And isn't its standard deviation 0.1? Well, let's do one of the basic ones. Let's suppose I decide to only use the mean, give or take 2 standard deviations. So the mean plus or minus 2 standard deviations. Can anybody remember what percentage of the data is in that range?
95.
Right. So I would be 95% confident that the population mean, because that's what this is estimating, right? It's trying to estimate what the population guy is equal to 65 plus or minus 2 times this guy, which ends up being 65, give or take 0.2, and that ends up being this number, which is what, 64.8, all the way up to 65.2. So if this was a real story with real data, I would be saying to you right now, I'm 95% confidence that the average height of Americans, all Americans, the population, is somewhere between 64.8 and 65.2. Do you see I've narrowed the answer down into a very small window, and I've also told you how confident I am that this is correct. Now, a side issue, if I'm 95% confident that this is true, doesn't that mean there are a 5% chance that I got it wrong? That the real answer is somewhere else, could be anywhere. And if I did the previous one, remember I did something like the 99.7% one, right? Remember that one? Isn't there still a 0.3% chance I am wrong? Now, what the moral of that story is that in statistics, you will never be able to be 100% sure. And if you do enough samples and you make enough predictions using those samples and this technique, in this case, aren't I going to get it wrong 1 in 20 times? I'm going to tell somebody, this is where the answer is. And it isn't, right? And people are going to come back and say, you told me a pack of lies, or you told me, you know, you made a mistake. And I'm going to say, sorry, this technique is not infallible. It's 95% fallible, if there is such a word as fallible, right? It will do a good job 95% of the time, but won't it do a bad job the rest of the time? And you live with that. And that is why certain things that we thought were true, because people did totally proper analysis and they came up with a number and they said, this is what we think the number is. And then later on, they discovered that they were wrong. Haven't they changed the goalposts on COVID-19 quite a few times? Like, what percentage of people catch COVID? And what percentage of the people who catch it die? What percentage of the people have caught COVID and asymptomatic, whatever you call it, right? They didn't even know they had it and they got over it without even knowing they had it, right? Do you know those are very important figures? Nobody I know can honestly put their hand in their heart and tell me any of those numbers. We are still in the early stages, right? Go look it up. What percentage of Americans have caught COVID and didn't know that they even had it? That data doesn't exist. And if somebody says it does, they're lying. Because do you know the only way you could really do that? Wouldn't you have to do a large-scale study and test everybody in it and find out those people who still had the antibodies from COVID-19 but never registered as being ill? And secondly, wouldn't you have to watch those people for 2 weeks in case they're about to catch it? Because the fact they've got an antibodies in it, couldn't that mean they're at the early stages of getting a full-blown nasty version of it? You see how difficult it is to get the data. So, yeah, they don't know, and nobody knows. We will know after the event, because after the event, and this is all over with, won't they have really good data because they'll have collected lots of it by then? And they will then tell us, only 20% of Americans ever caught COVID-19. And half of them never even knew they had it. And of the 10% that did catch it, this percentage of them ended up in hospital. And of that percentage that ended up in hospital, this percentage of them died. And you know that will not be the same number in every country. Don't catch COVID in a very poor country. Aren't the medical facilities not great? Isn't the medical treatment? If you're going to catch it in America. Don't catch it at all. But if you've got to catch it in America.
Well, statistically speaking, this is the only place you're going to catch it in the whole world at the moment.
Well, no, I think people in India are catching it quite well amongst themselves. And the Chinese are catching it quite well amongst themselves. So the only place you're going to catch in America is from Americans, you're right. But everybody in the world right now has got COVID to some degree or other, right? And some are on the way in, some are on the way out. But that's a different story. Right, so let me finally, for the last 25 minutes, or 30 minutes, whatever it is, let me try and give you some help on the last section of homework, which is called the central limit theorem, which is what we've been doing. And I'll do a view on this fella. The early part of it is, oh, you can't see it yet, so okay. I'll just keep the answers on. It's less hassle than taking it out and redoing it. So here goes. So this is your third and final section, 12 questions, so it's not too bad. Now, some names. Do you know the standard deviation of your sampling distribution? Do you know that sigma over root n guy, right? The standard deviation that I had? Here is called the standard error. Right? So the standard error of a sampling distribution is called the standard deviation. Right? That's one of your 12 questions out the way. Now, list two unbiased estimators. Unbiased estimators are basically things that we use to estimate what would be in a population. Isn't the mean a good estimate of the mean of a population? You agree? If I find the mean of a sample, wouldn't that be unbiased? Think of the word unbiased as meaning good, right? Wouldn't that be a good estimate of a population mean, right? And what would a bad estimate look like, right? A biased estimate. Suppose I decided to estimate the population of the ages of Americans by just finding who the oldest person in my sample was, who the youngest person of my sample was, subtracting them and dividing them by 2. Can you imagine me doing that? It'd be a really easy way to do it, right? Would you agree that that would be a bad estimate for the mean, right? So don't read too much into that. It's as simple as you would expect. Now, p hat is a guy we haven't done, but can you imagine you wanted to know the percentage of Americans who are going to vote Democrat? Wouldn't you use the percentage of people in your sample who said Democrat as your unbiased estimate? Wouldn't that be a sensible estimate? The percentage of the people in my sample who said yes to the same question. Now, describe the variability. I have talked about that. Remember when the sample size is 10 and when the sample size is 10,000, what happens to the standard deviation? Doesn't it become much smaller? The sampling distribution, standard deviation, becomes much smaller when the samples increase. And that's what that is saying. As the samples increase, the variability, you could say the standard deviation, because that's what doesn't standard deviation measure variability, right? How spread out data is. Now, question 4, I may have to notice this. If we have a distribution of X and that is more or less symmetric, what is the sample size N needed to claim that the distribution sample mean X from an ample sum is approximately normal? This is a number that has been created by statisticians, and the magic number is 30. What they're saying here is, if you want to do all the clever stuff with sampling distributions, right? You wanted to estimate the mean and do all that good stuff and do a plus minus thing on it. You need at least 30 people in your sample. Can you kind of think of why that's the case? Let's go silly. Do you think I could get good data by you just picking 2 people and finding their age? Would you agree that that could be all over the place, couldn't it? Wouldn't that be bad? How about 10 people, right? Well, 10's a better, right? But would you agree that 10 people could still generate some really weird answers? Couldn't I really get unlucky and ask 10 old people? And I would think the American population was full of geriatrics or 10 very young people. So the magic number here is 30. Now, this one's a little bit different. If the data, the population is normal, you can actually get away with any sample size. But if the data is kind of symmetric, actually, it's better than that. Do you know if your original population is skewed to the right, which is bad news? Do you know as long as the sample size is bigger than 30, you can still do it? But if your sample is normal, you are good. Oh, okay. Here's a quick question. Suppose you'd had a sample of size 100 and a different sample of size 225. Wouldn't the one with the sample size of 225 have a smaller standard deviation, right? Standard error is just the name for the standard deviation of your sampling distribution. And there is the funny way that they do it. They do sigma with a little x bar. I do not like that notation. I like just saying standard deviation. But see that funny sigma with an x bar next to it? That's their symbol. We're halfway through. Suppose you have a x as a distribution and the standard deviation is 24. And let me write that down. So I know that, what do I know here? That sigma is 24, okay? And x is our distribution. And we're being told that we need a standard error to be 2, okay? And in the next question, we need the standard error to be 1, okay? So let me show you how to solve that question. The guy that they're calling the standard error is also called the standard deviation of the sampling distribution. And it is equal to sigma over root n. Now in this question, sigma was 24, and we're told that we wanted it to be 2. So here is one of the few times that you actually get to do good old-fashioned math. Don't we have to solve an equation for n? Right? I guess I'll put it over here because I need more room. Anybody want to tell me the next line of algebra to eventually get the value of n?
You know, multiply 2 by the square root of n.
Okay, so if you do what's called cross multiply, something like that. Great. What do you do next?
Divide 24 by 2.
And here's something that people do, and I'm not quite sure why, but they do it a lot. So let me tell you what the answer is not. The answer isn't the square root of 12, which is about 3.5 roughly. What do I do to both sides to get from here to here?
You have to square it.
So you actually need a sample size of 144 people to get that standard error. Right. So what happens is you're about to start an experiment. You haven't asked a soul yet. And you want to do it cheaply, right? So you want to do it cheaply. So you don't want to ask more people than you need to. And typically you decide on how big you want that standard error, right? Do you want it to be 2, right? Do you want it to be more accurate? Do you want it to be 1? Do you want it to be really accurate? You know, you might want it to be, I know, 0.1, right? Now, for each of these cases, don't you have to choose a different sample size to guarantee that result? In this one here, didn't we have to choose 144 people? So that's how big you would go. And you'd say, right, you go to your boss, right? Whoever your boss is, right? To get the evidence that I'm looking for, I need a sample size of 144. And the guy's going to say, well, that'll cost us 10,000. And I'll sign off on it, do it. You don't want to just go and say, I want to do this survey, I want to do this experiment. 500 sounds like a nice round number. Can I get money to do it with 500? And the guy's going to say, well, I could, but I mean, how accurate do you want your answer to be? And you're saying, no, I don't really care. Plus or minus 2 is cool. Well, he's going to say, well, why don't you just do it with 144 people? Because that's what you're going to get. See, if you do it with 500, then you're going to get a better answer than you really wanted. A more accurate result than you really needed, let's say. Suppose you're doing it with 1 now. Won't it be that guy? Won't it be 24 is the square root of n? And that guy is 24 squared. And now we're talking well over 500 people. Now, if I call that doubling the accuracy, right, because I'm reducing it by a factor of 2, do you notice that I didn't double the population, the sample size? Didn't I go from 144 to 576? Isn't that more like 4 times the size? What do you think I need to be that kind of accurate? Do you think it's going to be in the thousands? Well, let's see. If you make that 0.1, 24 is 0.1 root n. Divide both sides by 0.1, you get that. And n is going to be whatever 240 squared is. Wow. Your boss is not going to pay for that. Do you know if you try to do a clinical trial with 57,600 people in it, how much that would cost? We are talking millions here. You understand? Literally tens upon tens of millions. The FDA doesn't even ask you to do experiments, right? Clinical trials that size. Because if you had to make that the going rate for a clinical trial, wouldn't there be a lot of medication never reach it to the market? Because the pharmaceutical company is going to say, that's going to cost me about 50 million, and it might not work. Can you imagine 50 million, right? It's a bit like chucking it in the bucket, right? It's gone, right? The medication, might end up not being good, right? You won't know until after it's done. If you're interested, do you know that the normal going rate for a decent sized clinical trial is? Do you know what they typically pick? Slightly over 1,000. They normally pick weird numbers like 1,026. And you might think, why 26 or 22, or why is it the extra few? When you do a clinical trial, any clinical trial, some people just drop out. Because you ask for volunteers and you get paid, depends on the trial, right? And some people drop out. And so the 26 is just like a buffer so that you're at least guaranteed 1,000. And that's because of, this calculation over here. To get a certain accuracy, you need a sample of 1,000. So you err on the side of safety and you pick 20 odd people more. Sometimes it has to be larger. And because if you're doing a clinical trial and it's on very sick people, don't some of them go and die on you? So you might need 1,200, if it's really serious, late stage cancer treatments. right? You want to have at the end of the trial 1,000 numbers, right? 1,000 people still alive, so you've got numbers with them. I mean, the people who die are figures, right? They are results that can get used, but it's better to have the trial clinically finish at the end, so you get an idea of what the full treatment does. Do you know some treatments are really effective, but the person's just so ill that they die before the treatment is successful, right? So that's a sad thing, but that happens. Right, let's return. I got 15 minutes. That's what's going on here. Can you see the calculations that I just did? See them there? Right. What have we got left here? 2, 3, 4, 5, 6, 7, 8. I'm scanning through to make sure I've got all these guys. Okay. I am now able to show you the last bunch of questions so that you'll be able to finish your homework off. So this is going to be the last time, I hope, that we'll need to switch pictures. So there are going to be two main kinds of questions here. The first one is we're going to get a sample. And the sample is, say, 300, because I want it to be. And we're measuring something, whatever it is, and I'm just going to call it X bar, and it's 53. And I'm going to be told the standard deviation. So for no particular reason, it's 14. And you're going to get some questions involving what the values of this might be. So that's the first question. So what's the percentage of times that you could get a sample mean greater than, I have to pick a number here that's pretty close to that, greater than 54, just for argument's sake. So if I was calculating using these numbers and this fella here, what would my standard deviation called? I'm going to have to use their notation, sigma X bar. Well, it's sigma over the square root of n. It is 14 over the square root of 300. And so I am looking at 14 divided by the square root of 300. And I'm calling it 0.8 to make my life easy. So what's my sampling distribution look like? Well, I know it's normal, and it has a mean, well, let's do it in English. It has a mean of 53, and it has a standard deviation of 0.8. So this question is now possible. What's the chances that I get a sample bigger than 54 from a distribution that looks like this fella? Well, isn't that a normal CDF? And in a normal CDF, you have two numbers, and you have a mean, and you have a standard deviation. Do you see that the mean goes here, and the standard deviation goes here? Right. Don't be distracted by it's called X bar. Just think of it as, what's the chance that I get a number bigger than 54? Well, won't that be 54,999? Aren't we returning back to the start? Right, what we did earlier today, right? Won't this fella here be the normal CDF of 54 or bigger with this mean and this standard deviation? So I'm going in here and I'm going to go second distribution. Let's get the guy, normal CDF, and it's going to be 54 or bigger. And the answer that I get is that it's going to happen about 11% of the time. So if I know the mean and standard deviation, either the sample mean, or sometimes they even tell you as a population mean, it won't really change the story, it's still 53. 11% of the time, I'm going to get a sample mean bigger than 54. Can you imagine that, I don't have time for this, but can you imagine I could also have asked you less than 51 and between 91 and 11, right? Wouldn't they also be normal CDF questions? Are you getting bugged by a fly, Olivia?
I'm irresistible.
Okay. Normal CDF. So those two guys go there, and then in this question, what it is, 53, and remember to use the 0.8, and off you go and you do the other ones. So that is the first kind of question, what's the chance that you get a sample bigger than, less than, or between something? And you get it by finding the mean, because I'll tell you, and the standard deviation, because I'll tell you, and that allows us to get this guy. And we basically just do a normal CDF. I think the major change is, don't you have to make sure that it's this number that you use and not that number? That's pretty much the only place I think you might get a little bit lost. And I'm going to do something before I forget. So I'm breaking my own rule of that's the last time you need to do that. I need to take an attendance picture. Okay, now we can get back to our question. So far, so good? So if you are given a story, what's the percentage of samples that are less than a number, between a number, or bigger than a number? This is the process. It's really a lot of overlap. Second kind of question would be something like this. What sample mean would be the 20th percentile? Well, I know the mean that we're going to use. It's 53. I know the standard deviation what we're going to mean. Okay, I'll put that notation in, but I prefer this notation. Do you recognize what buttons on the calculator answer those kinds of questions? Because we did that today as well, didn't we? What mean would put you in the 20th percentile? What sample mean would make you the 20th percentile? Well, it is a long day. I sympathize with you. Remember inverse norm? That's what I'm getting at. Now, to be the 20th percentile, won't we use 0.2? Won't we use the sample distribution mean and the sample distribution's standard deviation? And then I'll just zoom into my calculator and do it again for speed purposes. If you put 0.2 with a mean of 53 and a standard deviation of 0.8, you get the answer 52.3. So if I got a sample mean of 52.3, that would be in the 20th percentile. So that's on the lower side of my estimate. Can you imagine that's where the bottom 20% of my estimates are? You could get variations on a theme here. Couldn't they say what X bar is in the top 10%? So what sample mean is in the top 10%? That is also an inverse norm. But that's not 0.1. If you're in the top 10%, what percentile are you?
90th.
And so 0.9 goes there. You see how that's going to work? So there are three parts to this. I've already done questions where you're asked things like, what percentage of your samples are bigger, less, or between a number. And that's always going to be normal CDF. And these guys give you that. And won't the two numbers at the end be 53 and 0.08 or 0.8? And then aren't the percentile questions going to be inverse norms? That's going to be the decimal percentile. And won't these still be 53 and 0.8? So what's the last question that you could be asked? Suppose I tell you that I have a population and I know the mean is 30 and I know that the standard deviation is 20 for whatever reason, right? I could ask you this question. What's the probability or the percentage that I choose one person, not from a sample, but just from the population, and that person has a value bigger than 39. Now this would actually be written like that. Now you notice that is not the same as that guy. If you look really carefully, do you see that's an X and do you see that's an X bar? Now that makes a big difference. X means population numbers. So if I'm doing this one, won't it be a normal CDF? Bigger than 39 is 39,999, but won't the mean be 30 and the standard deviation be 20? If it was this story, the mean would still be 30. And wouldn't the standard deviation have to be calculated? And in this story, it would have to be a sample, right? Say 200. So the standard deviation would have to be 20 divided by the square root of 200, which is why we have calculators. And this ends up being, that looks wrong. Oh, it is wrong. It's 1.4. Okay. Now, in this case, that's what we do. In this case here, it would also be a normal CDF. But it would be 39 again. It would be 999 again. And the mean would still be 30. Wouldn't the only change be the standard deviation? Now, this guy I'm about to do, and then this guy I'm about to do, and they will be really weirdly different in size. So I'm doing 39 or bigger, a mean of 30 and a standard deviation of 20. And this answer is going to happen about 33% of the time. So if you just pick one person at random from the population, what's the chances that they're bigger than 39? And the answer is about 33% of the time, that's what's going to happen, right? You're going to pick a person bigger. Let's look at this fella. What's the chance that you take a sample of 200 and the average of them is bigger than 39? Now, would you agree getting an average bigger than 39 is a lot harder than getting one person bigger than 39? And if it's a lot harder, shouldn't it be a much smaller percentage? So here it's 33. What do you think this might be? 3%? 0.3%? Well, let's find out. It's going to be a normal CDF, a 39, a 999, a 30, and a 1.4. And the answer I got is roughly 6e to the negative 11, which means 6 times 10 to the negative 11, which means 0.1, 2, 3, 4, 5, 6, 7, 8, 9, one more, 6. For all intents and purposes, wouldn't you say that that's basically, it ain't going to happen? when you take one number from a population, it's not too unlikely, right? It can happen that you can get an extremely big value, right? One extremely big value. Isn't it really difficult to get a really big mean? Because to get a really big mean, don't you have to have lots of big numbers? But a couple of big numbers isn't going to make the mean move too much, right? Unless it's a Bill Gates number. And